All right, my name is Jon Zysk, and this is for Dynamics Project 1, and we are part of Group Lantana. And let me go ahead and share my screen, and I'll start my part of the presentation. All right, so like I said, our group is Lantana, and it consists of Corbin Boss, Kyle Briscoe, and myself, Jon Zysk. And I created this today, September 22nd on 2021. Our problem statement was a person launches themselves into the air towards a landing which is 1.5 meters above ground level at a distance which is 4 meters from the release point of becoming airborne. What initial velocity should be used to make it to the landing? And there are going to be 4 different scenarios that will be explored. I'm going to share my 2, and the other 2 gentlemen will share theirs. The equations that we're going to use are going to be x equals the initial velocity of t times cosine theta, and y equals the initial velocity of t times sine theta minus 1/2 gravity times t squared. So for scenario 1 is a person jumps from an in-ground trampoline with an initial angle of 65 degrees. What initial velocity is needed in order to make it to the landing, where t is time in seconds? And here we have a crude drawing of a person jumping upwards at a 65-degree angle, in which they have to clear 4 meters in the x direction and 1.5 meters in the y direction. So for the solution, we use the x equals initial velocity of cosine theta times t, which transfers to 4 meters is equal to initial velocity cosine 65 degrees times t. From that, we get 9.46 meters divided by the initial velocity is equal to t, or the initial velocity is equal to 9.46 meters divided by t. From there, we go to y is equal to the initial velocity of sine theta t, which transfers to 1.5 meters equals the initial velocity of sine 65 degrees times t, minus 1/2 of gravity times t squared. So working that out, it comes down to 1.5 meters is equal to 9.46 meters divided by t times sine 65 degrees times t, minus 1/2, 9.81 meters per second squared times t squared. Now the t in the first part of the equation cancels itself out, and we're left with 1.5 meters is equal to 9.46 meters times sine 65 degrees minus 4.905 meters divided by meters per second squared times t squared. Reducing that down, we get 4.905 t squared is equal to 7.07, and t squared is equal to 1.44 seconds, or t is equal to 1.20 seconds. Now, if we put that into the equation for the initial velocity, we get the initial velocity is equal to 9.46 meters divided by 1.20 seconds, making the initial velocity equal to 7.88 meters per second. So in conclusion, in order for the person jumping from the in-ground trampoline to make it to the landing 4 meters away at a height of 1.5 meters, that person would have to be moving at an initial velocity of 7.88 meters per second. For the second scenario that we came up with, it is a person jumps from a swing with an initial angle of 45 degrees, launched from 1.8 meters above ground level. What is the initial velocity required to make it to the landing? And I failed to add the 45-degree angle mark on the drawing, but I did want to show that they are 1.8 meters above the ground. They still have the 4 meters to go, and the landing is still 1.5 meters above ground. And so we use the same equations for the solution. So it's going to be x equals initial velocity times cosine theta times t, which transfers to 4 meters is equal to an initial velocity of cosine 45 degrees times t, making that 5.66 meters divided by the initial velocity is equal to t, or the initial velocity is equal to 5.66 meters divided by t. Then we move on to y is equal to the initial velocity of sine theta t, which turns into 1.5 meters minus 1.8 meters is equal to the initial velocity times sine 45 degrees times t minus 1/2 gravity times t squared. From that, it transfers into negative 0.3 meters is equal to 5.66 meters divided by t times sine 45 degrees times t, which will cancel out, minus 1/2 times 9.81 meters per second squared times t squared. And so from that, we're going to get 4.905 t squared is equal to 4.30. Therefore, t squared is equal to 0.877 seconds, or t is equal to 0.936 seconds. Applying that value for t into the equation for the initial velocity, we get 5.66 meters divided by 0.936 seconds. The initial velocity is equal to 6.05 meters per second. So in conclusion, in order for the person jumping from the swing at an initial height of 1.8 meters above ground at an angle of 45 degrees to make it to the landing, which is 4 meters away, that person would have to have an initial velocity of 6.05 meters per second.